Hello GCA candidates, so welcome back to School for All and also welcome back to our last physics class of the year. So today I decided to do my last physics class on option 3 electronics. Yeah, I received many messages concerning the option. So those that are not doing electronics, really sorry for that, because I also received messages concerning energy resources, concerning communication and all those things, but I prefer to do electronics because I think that one is the most challenging option. Okay, so today we'll work on a sample GC equation, a mock. I really like this mock because it's taking the overall note. So while answering the mock will really help us to revise. Okay, now the first question, option 3 is always question 10. We are asked, a semiconductor can be doped with donor impurity atom or acceptor impurity atom. So we first of all know what is the meaning of doping. What is the meaning of doping? We are doping. So doping, you know that doping is adding what? Some impurities to a pure semiconductor in order to what? In order to increase its conductivity. So that is the meaning of doping. Now, why doping? We can do it now with a donor or with a donor impurity or an acceptor impurity atom. Is okay. Now, most of the time, donor impurity atom are those atoms coming with what? More electrons. Example, when I'm doping with a pentavalent, a pentavalent atom will be a donor. A pentavalent atom will be a donor because it's coming to what? It's coming to dope, and it's coming to dope a pure semiconductor. And we also know that a pure semiconductor has silicon, which have how many electrons? 4 electrons. Pentavalent is having 5. So it's coming to dope a pure semiconductor with how many? 5 electrons. Therefore, it should be a donor. It's okay. Pentavalent atom will be donor impurities. And for acceptor impurity will be trivalent atom. Trivalent atoms are called acceptor impurities because they are coming to dope with less electron than the pure semiconductor. They are coming with 3 electrons while the pure semiconductor is having how many? 4. Therefore, he's not coming to give, he's coming to accept. Okay. Now we are asked to distinguish between the two in terms. We are asked to distinguish between a donor atom, a donor impurity atom, and an acceptor impurity atom in terms of first. The first one is in terms of majority charge carriers. Majority charge carriers. Now, in terms of majority charge carriers, student, you see that what? A donor atom, the majority charge carrier there will be what? Electron, because it's coming with more electrons. So more electron will be found in the pure semiconductor. So here we have what? More electrons will be formed. So the majority carriers are what? Electrons. Let me put only electrons. And here for this is for donor electron. Now for acceptor, since the acceptor is coming with the acceptor is coming with 3 electrons, so it is lacking 1. Therefore, holes. The majority charge carriers here will be holes. As easy as that, you have your 1 mark. Now, if I want to distinguish in terms of semiconductor form, if you want to distinguish between in terms of semiconductor form, you see that what? A donor, when I will dope a donor atom with a pure semiconductor, I'll have what? More electron than holes. And it is which type of semiconductor with more electron than holes is what? N-type semiconductor. N-type. And when I will dope now with an acceptor, when I will dope a pure semiconductor with an acceptor, I will simply have what? A p-type semiconductor. Why? Because it's p-type semiconductor. Why? Because in a p-type semiconductor, we have more holes than electrons. So that is it. I always told you, if you want to remember p coming from proton, positive, holes are also positive. So when you have p, remember what? P has more holes than electron. Then If P is more holes than electron, therefore N should be more electron than holes. That is as simple as that. That is the first part. That is the A part of our equation, Roman 1 and Roman 2. Now let us go to interesting part. B part of our equation, we are having two diagrams. We are having two diagrams. Let me draw it very fast. So we are having this diagram. We are having this diagram. Okay. We are having this diagram. Okay. I think you first of all identify. So this is a diagram. This is a transistor. I think you know this is a transistor here. This is it. And you should know that this is the base, collector, emitter. So this is an NPN transistor. Why? Because look at, the emitter is like this. If it was like this, if the emitter was going upward like this, therefore this one will be PNP. So people should note it. Okay, so this is the diagram of a simple circuit. Okay, the diagram of a simple circuit with a transistor. Okay, we are having another diagram. Okay, I will draw it after. Let me first of all see the question they are asking. So Homer 1, sketch the output characteristic of the transistor showing the variation of collector current IC with the collector emitter voltage VCE for different constant values of the base current IB. On your sketch, clearly indicate the active region, saturation region, and cutoff region. Okay, that is good. That is the reason why I wanted to take this question here, because it's touching important part of the note. Okay, it means that what I want to come out with the output characteristic of a transistor. Is okay. I want to come out with the output characteristic of a transistor. And what you should know, student, is that for us to come out with the output characteristic of a transistor, there's a specific diagram, there's a specific circuit diagram for us to come up with the characteristic of the transistor. Output characteristic, transfer characteristic, input characteristics. Is okay. So sometime in some question they will ask you come out with the diagram which make it possible to come out with these characteristics. You should know it. The diagram is quite easy. You have your transistor here. Let me show you the diagram that enables us to come out with the output characteristics of a transistor. You should have something like that. You have your resistance here, and then you have what? A potential divider here like this with a PD here. And same thing here, you have a resistor here. It's connected all through here. Then you have another potential divider here. That is all. So that is it. There is RB, there is R load, potential divider here, there is voltage here, another potential divider here. So that is it. So this is a circuit that permits us to come out with the output characteristic or the transfer characteristics. In fact, the transistor characteristics is okay. When you're talking about transistor characteristics, we are talking about what the different graphs that gives us what the variation, how the different components of the circuit varied with each other. Now let us come back to the output characteristics. So I wanted to come out with a diagram because in some question they will ask you. So this is it. As simple as that, you come out with a diagram. It's not difficult. So the output characteristic here, output characteristic of the transistor, output characteristic of the transistor, it is a graph. It's okay. It is a graph showing what? It is a graph of IC against VCE. So showing the variation of IC against VCE at different constant values, at different constant values of IB, the current flowing through the base. So that is it. So the output characteristic is an IC against VCE at different constant values of the base. So this is how it look like. I will have something like this, where this one is what? IC, current. IC means current flowing through the collector. VCE is the voltage between, this is VO, is the same as VCE, V output. Is the voltage between what? The collector and the emitter. Then with different constant value of IB, it means that when IB maybe takes a value 0, no current will flow. If there is no current flowing here, no current will flow through. In fact, I will explain you why. No current will flow through the collector. Okay. Then I will have a different curve like this. I don't know if I will have different curve going like this. Straight lines. So this is it. So this is a sketch where these are different values of IB, 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 IB. Okay. So there is a sketch as simple as that. So for different values of IB, this is how the curve look like. For another value of IB, this is and so on. This is a sketch. And from the sketch now, you should be able to show which region corresponds to the saturation, which region corresponds to the active region, and which one corresponds to the cutoff region. Now people should look up. All this region here down, you should know that all this region down here, like this, all this region here represent what we call the cutoff region. Why am I saying that it's the cutoff region? Because when there is no current flowing in the transistor, it means that no current flowing at the base, there will also be no current flowing at the level of the collector. Look at, when there is no current here, there is no curve. It means that there is no current flowing at the level of the collector. Therefore, the transistor is going to be cut off. It's like an open circuit. No current flowing in the entry, no current flowing in the output. The output is the collector. It's okay. So that is it. Then this region here, this region is okay. So from here to here, this region is what we call the saturation region. Okay. So this is what we call the saturation region. Yeah. So here we say that the transistor is saturated. It's okay, and it can be used as a switch. Yeah, this property can be useful for a switch. Why am I saying that it is saturation? Because current already, IB exists already at this region. It's okay. It means that as IB is increasing, as the value of IB is increasing, you're seeing that even IC is also increasing. It means that different value of IB is increasing, making what? Value of IC to also increase. It means that the transistor is being saturated. It means that the transistor is on. Transistor is being on, therefore current now can flow through the output, which is the collector. Now from this, from here to here, or let me put it like this, here to here is called the active region of the transistor. So here, exactly when the curve becomes constant, is okay. Exactly when the curve becomes constant, we talk about active region. And at the active region, the transistor is being used as what? As an amplifier. It's being used as an amplifier. It is amplifying the signal coming. It's okay. And at the active region, the curve doesn't depend again on the value of VCE. It's okay. So there at the active region, IC is simply equals to a certain beta IB. We are amplifying what? The input signal. And the output signal should be a constant multiplying IB to show the amplification. Where beta here now should be what? Beta here now should be a current gain. So those are the different regions. This region, remember this region here represent the saturation region. Is okay. When IB already start existing, therefore we're having different value of IC. We say that we are on the saturated, the transistor is being saturated. It's already having current flowing through it. Therefore, it is saturated. It behaves as a closed circuit, so current can now flow through the collector. Now, down here like this, where there is no curve, we talk about cutoff region because no IB here, because IB here is 0, because IB here is 0, no curve exists, the IB is 0. Therefore, if IB is 0, the transistor is cut off, the transistor is off, no current will flow through the output of the transistor. IC is 0. Okay. Then between here and here, where the curve is already constant like this, is okay. So for this portion like this, from here to here, where the curves are constant. We talk about active region. There the transistor really acts as what? An amplifier. Is amplifying what? The input signal, which is who? The base, to have a collector current, which is who? Beta IB. So that is what they were asking for. As easy as that, you have your output characteristic. And with this output characteristic, we can even come out with what we call the transfer characteristic. With the output characteristic, in some question they will ask you to come out with a transfer characteristic with a given value of VCE. I can fix maybe the value of VCE here to be maybe, I don't know, 3 volts. And I ask you to draw the transfer characteristic for a constant VCE of 3 volts. You draw a straight line graph, exactly. Then you come here, transfer characteristic for a transistor. It is a graph showing the variation of who? Of IC against IC against who? Against IB for a constant value of VCE. Exactly. So that constant value, if it is 3 volts, I will draw a straight line graph exactly passing through that 3 volts. Anytime the line now touches the curve, I extrapolate like this. If the value of the current here maybe IB maybe is I don't know, 3 milliampere, you come and draw the transfer characteristic like this. You see that will be something like this. Here will be here will be IC, here IB. It is starting somewhere here like this. It's okay. And then you see that the slope under this graph will give us what? The current gain. We give us the current gain in bracket beta. As I say here, it's okay. We give us the current gain, which is beta. So that is it. As I was saying, when you draw your line, you come up with a table. When you draw the line, you come up with a table of IB, then IC. You come up with a table like this. Now, when the line touches maybe the first IB, if IB was maybe 0.03 amperes, you put 0.03 up, you extrapolate, you have the corresponding value of IC maybe, which is 0.4 amperes, and so on. It's okay. When you touch down the next line here, you take now it can be 0. It will increase 0.05 amperes. Down here will be 0.6. You extrapolate like this, you have the corresponding value of IC. From there now, you come and draw what? The transfer characteristic. This is it. And the slope of that transfer characteristic gives us what? The current gain. Okay. Roman 2 is with reference of our sketch in B Roman 1. Explain how the transistor operates as an electronic switch in a saturation and cutoff regions. Okay. As we did before, you saw that having one section of saturation and one section of cutoff is okay. And I told you that what? Those two regions of the transistor can be used as what? As a switch. Now let us start maybe with the saturation. A saturation region, let me show you how the transistor is being used as a switch as in the saturation region. In the saturation region, what you should know is that we say that saturation region because IB is large or sufficiently large. Yeah, IB is sufficiently large that it cannot turn on the transistor. So IB is sufficiently large, turning on the transistor. Is okay. So at saturation, IB is sufficiently large to turn on the transistor, making a large amount of current to flow. Through the collector. That is it. So it means that what? When the transistor is saturated, it means that IB is large enough to turn on the transistor. It's okay. So a large amount of current can now flow through the collector. We say the transistor behave. We say the transistor behave as a closed circuit, as a closed circuit. So that is it. So that is how we can use the saturation region to explain the behavior of the transistor as a switch. Is it okay? Now, without wasting time, let us go to cutoff region. At cutoff region, we now see that what? The current flowing at the base is 0. Is it okay? Current flowing at the base is 0. Therefore, the transistor is turned off. The transistor is turned off. Is okay. It means that what is entering cannot turn on the transistor, so the transistor will stay off. The transistor is turned off, so no current flows through the collector. As I told you, that collector is our output. So if no current flows through the collector, the output region of the transistor, it means that what? The input region, the signal of the input region was low. That is what? 0. Is okay. So turn off. So no current flows through the collector, and the transistor is said to be what? To behave as an open circuit. To behave as an open circuit. We all know that what? In an open circuit, current cannot flow. Is okay. In an open circuit, current cannot flow. So that is it. So that is how we can explain. That is how we can explain how a transistor operates as a switch using these two regions. Now, figure 8b shows how the input voltage Vi. Okay, so then now let us move to Roman theory. Figure 8b shows how the input voltage Vi varies with time t. Copy the graph and using the same time scale, sketch the corresponding variation of the output voltage VO with time. Okay. So let me first of all illustrate the graph here first. Now, this represents, it's a graph of what? The voltage which is being input against time. It's a graph of the voltage which is being input against time. Now we are asking us to calculate a graph of voltage output against time t. Now, you first of all understand something here. Here, the switch here can be used as a, the transistor here, this circuit can be used as a switch, and it can also be used as an amplifier. Is okay? Let us consider where it is used as a switch. It means that what? It is used as a switch, it means that it's having what? Two regions of operation. The saturation region and the cutoff regions. I hope you understand it. So, let me see how when Vi varies, how will V0 also varies. Now, let me come up with the expression of V0. To come up with the expression of V0 here, I will come and turn Kirchhoff here. Look up. Here, 0 voltage, 9 here means that current is going like this. If current is going like this, it means that the voltage across LR here should be like this. So if I turn Kirchhoff here like this, I'll have what? 9 volt equals to IC, because it's IC flowing here. The current through the collector, this is a branch of collector, ICRL, resistance of the load, then plus VO. When I turn Kirchhoff, I hope you understand it. Or you can see understand it like that. 9 volt here is a what? Is a supplier. He's supplying to who? To these two components, RL and VO. So 9 volt will be divided between the voltage across the load and the output voltage. Now this is the equation. This is the, let's say, the output equation. When you turn Kirchhoff at the output, this is the output equation of the transistor. From here, you see that as I'm using, let's say I'm using my transistor here as a switch. It means that there should be what? Two states. The first state is saturation. Saturation. At saturation, we know that what? The current flowing through the base is maximum. Is large. Or is not zero. The current flowing through the base is not zero. Implying what? Current will flow through the collector. Implying the current flowing through the collector will be maximum. A large amount of current will flow through the collector because this the transistor is what? Is on. The transistor is on. When the transistor is on, a large amount of current will flow through the collector because on means I can replace the transistor as what? A closed circuit. It means that current can flow. Therefore, a large amount of current will flow from the collector. And if a large amount of current flow through the collector is okay, it means that all the voltage drop. Look at IC is maximum. It means that V0 will be what? Slightly equals to 0 volts. Are we understanding? IC is maximum, making the voltage across the load to be maximum. The voltage of the load will be maximum. It means that all this 9 volts is being dropped here. This one is slightly equal to 0. Are you understanding? It means that V output is 0. Are we understanding what I'm saying? V output is 0. So this is saturation. And for us to be at saturation, how should be V input? V input should be what? 60. So at saturation, we all know that what V input is 60 volts. I don't know if, yeah, 60 volts. Is okay. When V input is 60 volts, when it is high, IB is 0, current will flow through the base because the voltage is not 0, current will flow through the base. Current will flow through the base. And making, if current flows through the base, meaning the transistor is now what? Turned on. We can replace this as a closed circuit. Therefore, a large amount of current can now flow from the 9 volts to the collector, making IC to be maximum. If IC is maximum, making what? The voltage across the load to be maximum. So all this voltage will be dropped here. V0 will be slightly equal to 0. Are we understanding? Now, when now VI now is what? VI, look at here. VI is not existing here. When VI is 0, we talk about cutoff. Here is the cutoff region. Okay, now let us go to the cutoff region, the other region of a transistor when it behaves as a switch. At cutoff region, you see that the V input here will be 0 volts. And if V input is 0, it means that the current flowing through the base is 0. No voltage, no current flows through the base. Therefore, we cannot turn the transistor on. The transistor will be off. When the transistor now is off, it means that no current flows through the collector. The current flowing through the collector is 0 amperes. And if the current flowing through the collector is 0 amperes, it means that no voltage across the load. Therefore, V output is simply equal to 9 volts, as easy as that. So at cutoff region, the input voltage is 0. So here, input voltage is 0. No base current, therefore no current through the collector, because no base current means that this transistor will be open. It behaves as an open circuit, and current cannot flow inside an open circuit. So no current will flow through the resistor, the load, yeah. And if no current flows here, IC0 here, no voltage here, therefore V output is simply equal to 9 volts. So that is it. From here now, I can come and draw directly below this my V output in voltage. Here 0, here is 50, here is 100, here is 150, here is time. It's okay. It means that what? When V in is 0, here is 30 and here is 60. When V in is 0, is okay. When V in is 0, how is V output? V output is maximum. Now, I was using 9 volts here, but normally you should take the value of 60 volts here. So V output will be maximum like this. We are here. This is the interval where V input is 0. So I will take the interval where V input is 0, but here will be maximum like this. Now, the interval where V input now from 50 to 100, it is what? Maximum here. V input now is maximum here. How is V output? V output is 0. It means I'll come back here. Now, the interval where this is what? Minimum. I'll come back here. Minimum, it means that V input is 0. No current will flow to the collector. The V output will be maximum. It means that I will have something like this, and so on. So this is the curve. Okay, so there is a graph, as simple as that. So when V input is maximum, V output is minimum. When V input is minimum, V output is maximum. I hope it's making sense, right? Okay, now let us move to the next question. The transistor is required to operate in a saturation when the minimum input voltage is 3 volts. Given that the biasing voltage for the BE junction is 0.6 volts. So they are just from giving what? They are just from giving VBE 0.6 volts. So that is the voltage between what? The base and the emitter. So the biasing voltage is 0.6 volts. Biasing voltage is 0.6 volts. Okay. Determine a suitable value for the base resistor RB. So Roman 4, we are asked to determine RB. I want to find RB. I'm looking for RB. Okay. Now, I know that what VBE is 0.6 volts. That is the information that I have. I also know that what? I also know that the current gain, they gave the current gain at the beginning 80. Okay. They gave RL, those are the information I need. RL to be 1.5 kilo ohms. Okay, we are looking for RB. Now, where is RB found? RB is found in the input region of my transistor, input loop. Is okay. So I will come and turn Kirchhoff here. I will turn Kirchhoff here to come up with the expression in terms of RB. I will come up with an equation in terms of RB. When I turn Kirchhoff here, I will see that VI is simply equal to what? The current flowing through RB is RB, plus there's a voltage here which is called VBE. The voltage of the base emitter, they gave it inside the equation, is 0.6 volts. From here now, I can know that RB now will be simply equal to VI minus VBE divided by who? IB. So that is it. Now I'm having VI. VI is how many? They gave VI to be 3 volts minus 0.6 volts divided by IB. But I don't have IB. I don't have the current flowing through the base. I don't have the current flowing through the base. Now, since I don't have the current flowing through the base, let me come and turn another output equation here at the output loop of the transistor. When I'm talking about output loop, I'm talking about what? The collector emitter loop. If I turn here, I turn it already, we saw it was 9 volts equals to IC RL plus VR V output. From then I can find the value of IC. IC will be 9 V output. Now we are at saturation. I even forgot. At saturation, as I was explaining, at saturation V output is slightly equal to 0 volt. Because at saturation, all the current is being what? Is being dropped here, making the voltage drop here to be higher than this one, very high, maximum, such that this V output is 0. So from there I have daily IC equals to 9 volts divided by RL. 9 divided by RL is how many? RL is 1.5 times 10 to the 3 ohms. So after numerical application, we have a 9 divided by 1.5 exponent 3. I'm having 6 milliamperes. So the current flowing through the collector is 6 milliamperes. That is 6 times 10 to the negative 3. Now, I have IC, but I'm looking for IB. The relationship relating IB and IC is what? IC equals to a certain beta IB. You should remember it all. So IC equals to a certain beta IB. So from here, another beta is what? The current gain, 80. Therefore, IB is simply equals to what? 6 times 10 to the negative 3 amperes divided by 80. So by calculating it, I will come up with IB directly. 6 exponent negative 3 divided by 80. I have 7.5 times 10 to the negative 5. So I'm having 7.5 times 10 to the negative 5 amperes. So that is the value of IB. Now with the value of IB now, I can now calculate RB. RB will be 3 minus 6 divided by 7.5 times 10 to the negative 5. Okay. So I will have 3 minus 6. 3 minus, pardon, 0.6. Here is 0.6, not 6. 0.6. So 3 minus 0.6 divided by 7.5 exponent negative 5, making the value to be 32,000 ohms. It's okay. You can still put 3.2 kilo ohms. So it can still be 3.2 kilo ohms. So that is the value of RB, as simple as that. It's okay. So nothing to fear in electronics. Calculations are very simple. I even like calculations. So let us go down to the last part of the equation, the C part. We are having a circuit. We are having the X, a box, the Y, like this. We are having the gate here, gate 1. We are having the hand brake joining here with another box, box 2, to have the output W. So we are asked, the system is functioning as an electronic logic gate. Define the underlying phrase. So what is the meaning of electronic logic gate? When I'm talking about electronic logic, an electronic logic gate here can be defined as what? It can be defined as a logic circuit. It can be defined as a logic circuit that performs a logical operation on one or more binary input in order to what? In order to produce a single binary output. As simple as that. So electronic circuit, it is an electronic circuit, which performs what? Logical operation on one or more binary input in order to what? In order to produce a single binary output. Then the next question is, name the electronic gate shown in the figure and draw the truth table for the system. Okay, so let us first of all understand what they are saying there. They are saying that a warning light W in a car is designed to be on if either of its two doors are open, that is one, and the handbrake H is off. Figure 10 is okay. It means that what? If either one door here is on, is closed, it means that the warning light is on when either is already on. So it is on when, so W here, should understand here that W is on when X or Y is high and handbrake is off. Off, it means H bar. If I take my handbrake to be H, so there is it as easy as that. It means that X or Y and H is off, therefore W will shine. So we have a high here when X or Y is on and this and the handbrake is off. So that is it. As simple as that. It's okay. It means that gate 1 should be the OR gate and gate 2 should be what? The AND gate, to join the two outputs. To join this one and this one, and we need AND. So that is it. Nothing to fear there, students. So then you can come out. We are having 3 inputs. They ask us to come out with a truth table. We are having 3 input X, Y, H. Those are the 3 inputs. And when we are having 3 inputs, I should start at 0, 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, here is 2, 2, 1, 1, 0, 0, 1, 1, 0, 0. Then here now will be 0, 1, 0, 1, 0, 1, 0, 1. Then after that, I should take now X or Y. Then I take H bar, then I have W. Okay, so that is how it should look like. Then X or Y, we all know that our OR gate is high whenever any of the input is high. So here I'm having already high, I'll have 1, 1,